page just to make sure yesterday's is down, because yesterday's was fairly labor intensive. And on a test, I only put maybe 2, but I think 1 of them, but they're worth a lot of points. So I want to, did I start early again? I'm sorry. All right, sorry about that. So I want to make sure that you know where all the points are coming from. So the first thing you do, right, is what you always do. You plug the 0 in, right? So we plug the 0 in. Are we all on this page in our notes? We're good? Did I give you enough time? All right. When I plug the 0 in, I get 1 plus 0, right? So I have 0 to the, and what do we say 1 over x is as x approaches 0? So it'd be like 1 over 0.1, then 1 over 0.01, 1 over 0.001, 1 over 0.0001, or 1 over 10,000, multiplied by reciprocal. So that goes to what? Go ahead and talk, guys. Infinity. Thank you. I think you're used to me when last year when I was recording, I said we're going to be quieter, but this year I'm not doing that because I record all the time. So go ahead and talk. They were really loud yesterday, and I loved it. All right, so this is 1 plus 0 to the infinity, or 1 to the infinity. Messes with your head that that's not 1, but deal with it. Okay, it's not. It's an indeterminate form. So we need to deal with, and the trigger I told them yesterday, because they actually, I don't know if I'm still recording, they flipped their worksheet 9 over, and I have Thomas's right here, so I'm just going to grab it. Did I say that in the video? Was I still recording? I said, let's flip to the back, and I said, which ones do you think you're going to use the new method on? Did I say that in the notes? Okay. And they spotted the ones with the x in the exponent. So that's how you know it's going to launch into this. All right, so in order to get it out of the exponent, what did I say to do in the note? So we rewrite it as e to the x plus x to the 1 over x. And we want to go L'Hopital, but we can't. So our first thing we're going to do is get that exponent out of there. What did I say to do? Well, Ryan. Natural log both sides. Yep, so that you can bring the power out front. And I'm not going to go as slow as yesterday because you should have watched the notes yesterday. Boom. Right? Then reintroduce the limit. So deal with the exponent aside from the limit, then reintroduce your limit. So as x is approaching 0, of the natural log of y is equal to limit x approaches 0 of. Now I'm going to kill 2 birds with 1 stone today because I showed them really slow yesterday. What do you think I'm going to do with this 1 over x instead of multiplying? Because L'Hopital's needs a quotient, right, Bodhi? So how am I going to write this? Natural log of the nicer, or the uglier function over what? Instead of 1 over x times it, I'll put it over x. Thank you. This is where I'm going to check and see. Now that I have a quotient, this is where a point comes in. I really do want to know which indeterminate form you get. So when we go plug that 0 in, bam, 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 right? When we plug the 0 in for the x, go ahead and do it in your head. What indeterminate form am I getting? Go ahead, Banana. E to the 0 plus 0, natural log, all over 0. 0 over 0. Yeah, because natural log of 1 is 0. So I really want to see that 0 over 0. Just make sure you don't write equal 0 over 0. Either write this off on the side or arrow it. All right, are you good? So next step, what did we say you do? Go ahead, Kate. Now what? L'Hopital and tell me you're doing the launch right there. I want to know, I want to spot it. Like, it should stand out. So then we'll L'Hopital this, Mason. What is the derivative of the natural log of u?
E to the x plus 1.
U prime, perfect, over
E to the x plus x.
u. Yep, and the derivative of x is just 1, so I'm going to take that bar off of there. Okay, now we plug it in. And if we get 0 over 0, we go again. But we don't. What do we get? Plug it in again, and you get, go ahead, tell me, Harvey. 2. And do you remember what I said? That's not your answer. Because you natural logged at the beginning, you need to undo that right now. So what's your answer? What is it, Catherine? E squared. Now, what number is E? Do you guys know? Like pi is about 3.141, blah, blah, blah. What is E? About 2.718-ish, which means that on this graph, I'm going to show you quickly, Did I go through that too fast, or are you guys good? You good? Thomas, you good? Witter, you good? All right, so I already have that graphed on decimals. Take a look. Everybody, eyes up here. This is the graph of that function. We found the limit as we approach 0 from both directions. There wasn't signage on there, right? We found that the limit was e squared. Guess what the y value is right here? 0, comma, what do you guess it is? E squared. It is. And e squared is about 7.1-ish, I think. And that's, I mean, if we were to zoom in on that, it's where it'd be. Make sense? Now, what if I had changed it to the limit as x approaches infinity? We're not, because it seems like you guys got that process, right? It looked good. I was looking out. What do you think my answer would have been based on this graph? As I approach infinity, we get the horizontal asymptotes. Definitely seems to be one, right? What would you guess it is? Looks like it's up at about 2 point. What do you think we would have gotten? Instead of a 2 and e squared, what do you think we would have had? A 1. And then, yep, I wanted you to see the graphical tie-in. All right, now some new stuff. Has nothing to do with that. You're going to need your calculators out. So grab your calcs. Take us about 20 minutes, and I think delta will take about 20 minutes, so we should be able to wrap the whole day up today. We're going in your notes. Actually, we're going to take a jump ahead. We're going to start improper integrals. So today is all about basically just what is one, some terminology. We're going to explore some stuff on our calculators, and then we're going to stop and go to delta math. All right, so an improper integral. You've never had one before. I'm going to put one up and watch where now, you guys, it's going to be dangerous. AB doesn't have to worry about this, but in AB, once we learn how to integrate, right, they'll learn that, hey, what is this? What's the antiderivative of that? You should know, right? What is it, Yoder? Natural log. Yeah, she's natural log, absolute value, x minus 1, and go from 0 to 2, right? Wrong. Now, you might say, what the hell? Heck, sorry. What the heck? Why is it all of a sudden wrong? Because this is called an improper integral. This graph has a problem. Where's, Katie just nodded, where's the problem? At x equals 1, what is there on the graph? You can't hop an asymptote when you integrate. Did you hear what I just said? You can't. Last year, you might have said, well, last year they told us that's because the bounds never resulted in that. So you were actually accumulating area under a smooth curve instead of trying to accumulate. Remember what integration is? It's area accumulation, signed area, right? But you can't find, there's an asymptote there. How do I grab a hold of it? That should really make sense. But do you see how deadly this is now? This is calc AB. That's calc BC. All right, so there's two kinds of improper integrals. One is like that, which is in my OR, and one is when one of the limits is infinity. It can be the lower one or the bottom one. Oops, sorry. The lower one or the bottom one. Too funny. Sorry about that. Or they can be negative infinity too. So kind of keep in mind when I write infinity, I mean plus or minus. They're easy to spot though, right, Mason? The minute you see an infinite bound, you're like, we didn't do that last year, and this is an improper integral, right? I'm going forever. How do I grab a hold of this area when I'm going forever? You might say, well, they're all infinity. They're not. That's what's weird. All right. So when one of the bounds is infinite, or when there's one of those discontinuities or an asymptote, right, for at least one value of x at or between the limits. So I'm just going to put an example of what I mean by that. Here's one where it's at the limits. That is no longer right now arcsine. Looks arcsine-y, doesn't it? But I'm at an asymptote, so I have an issue on the bound. Does that make sense? Here's an issue in the bound, 1 over 3x minus 2 dx from 0 to 3. You now have to spot that there's an asymptote, and you can't hop an asymptote when you're trying to collect area. All right? So those are both improper. One where the issue was at, and one where it was between at 2/3. All right? And they can lead you to false answers, by the way. So like if Bodie's like, I forgot, if he hops an asymptote, he might come up with an answer that's completely wrong because he's doing wrong math. All right. So let's go take a look at how we work with these. Here we go. This is a 1, by the way, down here. So do you guys remember what the graph of 1 over x squared looks like from last year? It was one of our parent functions, but it hasn't popped up yet this year. Do you remember what I called it? You're doing it with your hands. The volcano graph. Yeah. So if you were to graph that on your graphing calculator, 1 over 1 squared is 1, 1 over 2 squared is a 4, 3 squared, it goes like that. 1 over a half squared is 4. It makes this like that over here, and over here it goes like that. So it's the volcano graph. This is asking me to collect the signed area from 1 on out to infinity. Okay? So go like that. From 1 on out to infinity. It seems like we could use common sense, right? I feel like I skipped something. No. But doesn't your gut wonder say, well, I'm going forever collecting area, it's infinity. Right? Seems like that should be easy, right? There's an infinite amount of area under that curve. But that's not the case. So that's what's weird. Calc 2 is weird. All right? So let's go take a look at what happens. Let's investigate it on your calculator. All right? So this is what I want you guys to do on your calculator. Go to Math 9. We're not going to go to infinity. The first thing I'm going to have you do is Math 9 it from 1 to 9. So we're not even getting kind of close to infinity. But go Math 9, 1 over x squared dx from 1 to 9. And tell me what you get. I actually know what the answer is because I know how to do it. So you're going to be, but I don't want to say. All right? What do you get? 0.8 repeated. Okay. Let's go do that. Now I'm going to have you go second enter and pop that same one back up, okay? Arrow over and change that 9 to 99. Let's go closer to infinity. And this is what you're going to be doing in Delta Math. You're going to be scooting some sliders closer and closer. Then have you scoot the slider to have this top or bottom approach something, right? I'm approaching infinity because that's what it says. All right? What did you get for that one, Yoder? 0.9 with the just the 8 or the whole 9? The whole thing? Okay. Next, second enter again. We're going to do 2 more. We're going to head closer to infinity, but keep in mind, no matter how close to infinity we get, there's an infinite amount of more to do. But so we're going to stop at 4. Right? We're going to do 999. And it comes out 0.998 with the whole thing repeated, right? Okay. Now look it. I went way out there. Right? Let's one more time, second entry. Probably seen a pattern, but that's okay. Go ahead and do it one more time. I could play this game till I croak over and die because I can't get to infinity. At some point, though, your calculator's been programmed to bail. It's not here, though. It should still give you an answer here. What's it giving you? 0.9998, right? Now, I don't know how your calculator's programmed, so let's err on the safe side. Go try it one last time with a whole bunch of 9s. Okay, we're still not even close to infinity, but I think it'll be programmed to just round it. And what do you think it's going to round it to? Oh, wow. Well, isn't that it right there?
No, that's the bottom.
Oh, good Lord. So, it hasn't been programmed to bail. It it kind of broke it. Like that's not what happened. That's kind of interesting. I didn't know that. Maybe don't try as many. Try 5 of them. Maybe at too many, it just like goes, your calculator just, its brain blows up. Try 5 of them. What does that say?
4 9s.
Okay, try 6 of them. There's some point where I think it's going to bail and round it. I just don't know. I don't program them. I just use them. Try 6 of them. Is it still giving you all the 9s? Somebody keep playing until you find it. But the point of it is, what do you think your calculator is going to round it to at some point? Look at it. 0.99999999999999999999999999999. Forever, never, 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 never. Then there's going to be 8 and the repeat of our word. What do you think your calculator is going to round it to? 1. Okay? So it seems like we're settling at 1. And we do. The answer to that is 1. Weird, because I'm collecting area forever and I don't get past 1. Isn't that weird? But it's a limit problem, so we're going to approach these with limits. You can't treat infinity as a number. It's not 1. Infinity minus infinity isn't 0. Infinity plus infinity isn't to infinity. It's not an x, it's not a number, it's a destination that can't be reached. But you can try to get there. So we can have b approach infinity. I use b, some books use t. I don't like those because they look like pluses. I think Delta Math uses an a, so don't let the variable bug you. But you need to replace this with a number, and that number has to approach infinity. All right, so really it's a limit problem. This is what kids struggle with, is the notation. So that's why I'm putting an extra day in this year. It looked like that was 1. And it is. We'll prove it in just a second. But we say that that integral converges. So when you get a finite number that we appear to be settling at, we say it converges. So if you're doing the delta math and you come in and you get a 7.7, then a 7.8, and then a 7.99, then a 7.99999, right? You're going to say, oh, this converges to 8, okay? Now, if it went 7, 7.8, 7.9, 8, 12, 15, you're like, oh, it's not settling. So when you think converge, just think of it settling, all right? Next step, if the integral didn't settle, all right, so we're like, well, we didn't look like it's approaching anything. We say it diverges, all right? That means it's not settling. It's either going to infinity or negative infinity, okay? If you kept on going, it's just going to keep going and not settle. Does that concept make sense to you, Winter? So now here's the gist of it. What we want to do now is, all right, we saw graphically and numerically it seems to be 1. Now let's use calculus. So we're going to say we're going to go from 1 to b, because we have to go to a number. What did I say we're going to have b approach, guys? Infinity. We're actually going to integrate it. So I think I want to see the power. So let's write it as x to the negative 2nd. And this is what was helpful. The first couple years I didn't tell kids to do it like this, and they were always getting so lost in the notation. I said for a while, I mean, this isn't, you won't see it written like this, but I said put that part, the integral, in a box and work in the box. You're going to keep writing limit, but you're going to ignore the limit till the end. So you're just going to pretend that, those of you at home, I'm covering up with my hands the limit. Just integrate that like you always have. Add 1 to the power. Divide by the power. Right, Mason? Add 1 to the power, you get an x to the negative 1. Right? And divide by that power, you get a negative 1. So if you don't mind, I'm going to write it as negative 1 over x. You okay with that, Daniel? Are we all good? I'm still covering up the limit, you guys at home. Okay? And I go from 1 to b. Nothing changed, Noah, except that I have a variable in the exponent, but that's nothing new. Now, we'll put the limit back on. So just do your work as if the limit's not there, but don't forget to keep tacking it on. So do this as you always would. What do we put in first, the top or the lower boundary? Top, you still will. So ignore the limit again. And again, those of you at home, I'm covering it up. You're going to do negative 1 over b minus negative 1 over 1. Did I give you enough time to look at that? Harvey, you looking up? Are we good? Go ahead and, over here, right, whoops, sorry. After you put the boundaries in, right? Now put that limit back on. B is approaching infinity. So kind of just do it, Maya, like you've always done it, but keep that limit going. Now send B to the moon. If B goes to infinity, what does this approach? -1 over a gazillion. What's it approaching? Yep, you're doing it. You guys can talk. I know you're conditioned to not talk while I record. But it's fine this year. We got to. Otherwise, you're too quiet. The other classes picked it up. They get nice and loud. All right. So what does this approach?
0.
Thank you. 0. What's 0 minus -1? 1. So we did it graphically. We did it numerically, right? And now we just showed it with the calculus. This is how you're going to need to show it. But there's a pattern to this. So let's see how well you get it. So since this settled, we'd say it converged. And again, if it didn't, like if I work that out, which I'm going to do on in a little bit, that's infinity, we would say it's divergent or it diverges. All right. So this is what I already told you. I just have it typed up nice. So next up, it doesn't matter if you know how to do this if you don't know if they're improper or not. This was a 1, by the way. It looks weird. So let's just play the yes-no game. This one right here. Improper or not? What do you think? What do you think? You're shaking your heads, right? No, there is an issue, but it's at 0. It's not on or in the interval. That, calc 1. Natural log of 2 minus natural log of, the answer is natural log of 2. Right? This guy, improper or not? It's easy to spot that one, right? Because of the infinite bound. The next one, improper or not? This one. What did you say, Witter? Improper. Because on the bound, I'm at an asymptote. I'm trying to accumulate area under an asymptote. This one, improper or not? What do you think, Daniel?
Yes.
Yes. Where's the issue?
X equals
3 halves, there's an asymptote. It's on the interval, right? This one, improper or not? Definitely. And it's not because of the bottom. Natural log of 1 is fine. It's 0, right? It's an infinite bound. It's asking me to collect all of that. Now, what does your gut tell you that is? Divergent or convergent? Pretend I'm going forever. Here's my x-axis. Here's my natural log function. Going up and up and up and up, right? What do you think the answer would be? Divergent. Yeah, it means just common sense. So sometimes common sense is the winner. All right, so now we're going to investigate and then go to delta math. So I'm taking that last 1 over x squared, and I have almost the same problem. The only difference is the last one was 1 over x to the second, and this is 1 over x to the first. We're going to do it the exact same way. Are you ready? Its graph is super similar, too. So it's like this. It's just a little bit more above. Let's on all of these talk about the point where x is 4. Okay, but let's go from 1 on out and go shade that. This point here would be the point 4, comma 1/4. Because it's 1 over x. That's the one I'm doing right now, right? Now, Katie, on the last one, it was 1 over x squared, right? So it would have been 4, comma 1/16. You notice how the last one, even though it had the same magic just happened. Although it had the same shape, the 1 over x squared one would have been at like 4, comma 1/16. It actually came, don't graph this on yours, but it went like that. So they look similar, but they're different. One is closer to the x-axis. So what we're going to do with the 1 over x, it's going to ride above this red one that we just did. Let's go see what happens. Does it settle? Here we go, same thing. You're going to say I can't use infinity as a number. You're going to go from 1 to b. You are going to take the limit as b creeps up on infinity of 1 over x dx. You're going to ignore the limit. Blake, ignore the limit and just antiderivate. What's the antiderivative of 1 over x? Go ahead. Natural log. So he's still going to go the natural log of x, right? He's still going to go from lower bound to upper bound. The only difference is we have to treat this as a limit. How are we doing, Catherine? We've always plugged the top in. So we will. It's a b. It's ln b minus ln1 Am I going too fast, Nora? You got it. I really want you guys to finish in class today. So this is going to be the limit as b approaches infinity. Now that you're done integrating and using your fundamental theory of calculus, go to infinity. What is the natural log of b as b approaches infinity? Go ahead. Infinity. Yes. That's actually infinity minus, and what's the natural log of 1? Go ahead. Natural log of 1? 0. So this one is infinity. What it means is under the black curve up here, under the curve of y equals 1 over x, it will not settle. But under the red one, which is really similar, it did, and it settled at 1. Put that in your head, right? This one we'd say diverges. By the way, whenever you get infinity plus or minus anything other than infinity, it will diverge. If you got infinity plus infinity, it still diverges. This is an issue in a couple days, because what is infinity minus infinity? I don't know, right? So next up, we're just going to go play with that exponent a couple more times, and we're going to come up with a rule we're going to use. So now this, I don't know why these come up, it looks like a P, it's a 1. All right, so this guy is x to the 1/2 in the denominator. 1 over x squared converged to 1. 1 over x diverged. What does your gut tell you 1 over the square root of x will do? Let's go back to the graph. I'm going to go blue. 1 over the square root of x. I'm going to, because sometimes your common sense, guys, is a lifesaver on multiple choice. So if I went up here and instead did 1 over the square root of x, I'd be at 4 comma 1/2. It'd be above the black one. It'd come like this. What do you think happens if you're above a divergent? What do you think you do? Diverge, right? You have to. So we will get divergent for this one, but let's go run through it really quickly. I'm going to go a little faster now because I want to save some time. We're going to take the limit as b approaches infinity of the integral from 1 to b of x to the negative 1/2 dx. Are you good, Catherine? We're going to antiderivative as usual. Add 1 to the power. Divide by that power. Boom. From lower bound to top bound. Boom. Right? Limit it as b approaches infinity. Boom. This is 2 root x, really. That's what the half power is, right? Whoops. Whoops. All right. So this is going to be 2 root x from 1 to b as b approaches infinity. What do you think 2 root infinity is? Infinity minus 2. What is it? Infinity. This one diverges. I knew I was going to, though. Okay? Now we're going to play with it one last time. Okay? We already did this one, so I'm not going to redo it. It converged to 1. Go ahead and write that down. It actually converged. Well, just no. Leave it like that. All right. Here we go. By the way, these are all 1s. Now I'm going to bump the power up 1. And I'm going to go back to that 4. Okay? If this was 1 over x cubed, let's put my 1 here. Now this would be 4 comma 1/64. It's even closer to the x-axis than 1 over x squared was. Do you think it's going to converge or diverge? 1 over x squared went to 1, right? This one's even riding lower. So you think it's going to converge or diverge? What do you think? Converge, right? If you're under a convergent, you converge. But to what is the question? So let's go, we're going to do this one pretty sloppy. Are you okay with the notation? Can I go sloppy a little bit? So here we have x to the negative 3rd, right? And we are going to, I'm going to use infinity as a number. It's deadly, okay? Don't ever do it when you're doing free response, but I'm going to just keep that 1 to infinity. I'm going to be naughty, okay? I'm going to antiderivate as normal. I get x to the negative 2 over negative 2, right? I get negative 1 over 2x squared. From 1 to technically b as it approaches infinity, but I'm just taking a shortcut because I want to get you to your homework. All right, now look at what happens. All right, we have negative 1 over 2 times infinity squared minus a negative 1 over 2. Are you looking? Katie, what does this go to? 0. So what's my answer? It converges to something less. It should, because it's below it, right? What did it converge to? 1/2. Let's go write that up here. 1/2. Now watch me change the numbers. Everybody watch this. You don't do it, okay? Just watch, and then I'm done. I'm going to go purple, and I'm going to do 1 over x to the 4, so don't even write anything. You ready? Watch. This process, which is naughty, we get it, right? It's naughty. But watch. 4. Right? Well, then that becomes x to the negative 3rd over 3, or negative 1 over 3x cubed. Right? This would be negative 1 over 3 infinity cubed minus negative 1 over 3. So let's see if we can figure out what's happening here. What do you think it'd be if that was x to the 7th dx? 1 over what? Almost. 6. It's 1 over the power minus 1. Right? So that would actually end up being 1/6. So here's my conjecture. Ready? The integral, and I'm not going to prove it, from 1 to p of 1 over x, 1 to p, 1 to infinity, 1 over x to the p dx. What is that? Here's, and I'm not proving it, I just showed you a zillion ways. But it converges when that power got bigger than, it converged with a 2 and a 3 and a 4 and a 5 and a 6. But with a 1, it diverged, right? So for p greater than 1. Also, it converged to 1 over p minus 1. So when this was a 3, it converged to half. When this was a 5, it converged to a 4. It diverged when p is less than or equal to 1. We're eventually going to call this guy in the box the fence for divergence. You diverge at 1 over x to the first, 1 over x to the 1/2, 1 over x to the 1/3, 1 over x to the 1/4. Those will all diverge. The numbers above converge as it gets closer and closer. All right, we're done. Open up delta. And I'm going to steal somebody's first problem in the second set. Well, actually, just go ahead and work through the first set. When the first person to get to the second set, there's just 2 sets, and it's the second set that I'm most concerned about. There's 4 problems in there. How many did I put in the first set? Just 3, I assume? Yeah. There's 3 in the first set. Those are just, you don't really have to do much except pull sliders and investigate. So you might get the first one wrong, but then you'll pick it up. I'm going to see when we get to, and that's all we have for tomorrow. So finish that today if you're done for the day. So you're going to do exactly what it says to with those sliders, and you're going to watch. Oh, by the way, how many decimal places do you think we're going to be typing into those boxes? 3. Yeah, Thomas, I don't know if you required last year. AP requires a minimum of how many decimal places? 3. All right, so, and the guy who wrote this program's at AP. So it'll accept 3 decimal place rounding. You don't have to type the whole thing. Does Delta allow you to copy? 2 to 7. On the sliders. Type it in. Watch the area accumulate as you go. Move the bounds around. If you're struggling with it, let me know. It's kind of we haven't done a delta like this one before where you're pulling on the limits. 3 decimal places for -4 to 1. Oh, it did allow you to copy. Perfect. I guess it is allowing copy paste, so that's kind of where you can type it. Yep. So it's some function you don't even know what it is. you are supposed to go from -6 to 3. So you're gonna find the one with the lower bound of -6. You're already at 3. So you're gonna type in -6.316 into that box. You might not use those yet, it might be later. Everybody has a different problem, so I'm not sure what you'll use. Once you get one green X, you'll get a green check. I almost wasn't going to assign this because I was like, how's this work? But then once I did, I'm like, oh, it's actually. Go back up here to see. You see what I mean? Thomas, the answer to your question is you use it on the very final one. If you decide it converges, then you go back to this one and say, oh, it converges to 6. Whatever. You know what I mean? Let's go down and see what it says. The limit from -6 to b. So let's go back up. Did you fill in all these examples? Go finish those two. To 3 decimal places. You can round or truncate. Accept it. You can make it, was it 4999? So you can make it 40, or I think you can make it 399. There, you got one. Now you get the other two really fast. Once you figure out how to work the program, the learning comes on the second two you do. The first one's going to be trying to figure out what to enter, and then once you get it. So when someone has all 3, we're going to stop and go to their first one in the next set. Do you have one yet? Almost. Maybe 4 to 1. Pull the slide back. 4 to 1. Oh, it was +1, wasn't it? Sorry. There it is. Right there. They were saying that it was copy and pasting for the 2. So. So you have to watch your answers as you approach the number and see if oh, you already got one. Okay, let's just check this on the size over here. I'm not gonna read it. So you went from -6 to 3. I'm assuming you just grabbed that up and pull the slider. And then you went from -6 to 3.9. Assuming you did the same thing, right? You got a -6.94. Then when it went to 3.99, what was that should be okay. That should be okay. So when we go from -6 to b, as b is approaching 4 from the left, so that's this, we got closer to 4, and then even closer, right? Watch. This is getting, does it seem like it's converging? -6.316, then -6.948, and then 6.9, yes. My guess is it's converting to maybe 6.94 or 50. That's what we're over here, Susan.